we present discovering fatigue movements for virtual character animation. Our work is the first reinforcement learning-based approach that explicitly models full-body virtual character fatigue as shown here, where the character adapts its movements over time depending on a level of fatigue. For example, note the change in the performance for this kicking motion. One can observe that the jumping height of the virtual character decreases with increasing fatigue. Importantly, our method learns to adapt the motion without actually seeing different levels of height during training. In general, generating realistic-looking virtual character animation is a long-standing and challenging problem in computer graphics, games, and movies. It is especially challenging when the generated motions should show variations and allow for interactive control. However, most existing work has focused on creating variations in terms of style or slightly different movement patterns. Not much work has been done on physiological changes over time, such as becoming tired. To this end, we present the first deep learning-based method to faithfully synthesize fatigued movements and behaviors over time, without having to capture different levels of fatigue, as fatigued variations of stunt-like movements may result in injury. Despite its biomechanical and physiological importance, not a lot of research in modeling and synthesizing fatigued behaviors has been done. The most closely related works to ours that do try to simulate fatigue over multiple repetitions require capturing infinite variations when using kinematic-based models, or when using physics-based models require expensive musculoskeletal simulations, or careful tuning of maximum torque bounds and reward parameters. Furthermore, the two physics-based models have only been applied to carefully crafted, single-limb settings with limited movements. In addition, none of the mentioned works indicate the emergence of rest behaviors to the same extent as our method. To tackle these problems, we propose a two-step learning approach. First, we leverage imitation learning to train an expert policy to perform the given task. Second, we learn a fatigue policy by limiting the generated constant torque bounds based on the current fatigue level of a three-compartment controller model from biomechanics literature. Our method enables the automatic emergence of realistic rest and recovery behaviors and motion variations. We do not need to model muscle tendons explicitly, nor require captures of all infinite variations. We are able to generate interactive experiences such as a drop in performance, change of style, and compensation of forces without the need of additional motion capture data, motion blending, the need of an expensive musculoskeletal model, or carefully handcrafted torque limits and reward signals. The policy can further generalize to novel fatigue and recovery parameter combinations during inference, as a single combination alone already corresponds to multiple levels of fitness over time. The network can synthesize and discover unseen rest recovery and realistic movement degrading behaviors. For example, waiting behaviors, loss of height during jumps, slowing down of movements, reducing the number of successful tasks within a period of time, or change of stacking abilities during a backflip. After the agent has regained enough strength, it is able to recover and continue with the task at hand. Our method can easily be extended to goal-driven tasks, such as running towards certain directions, or even to different morphological characters, as long as a measure of torque or force is given. We show that not including fatigue into the observation space leads to unrealistic low-fidelity movements, and using no stiffness modulation leads to jittery and stiff joints during fatigue. We further show that a reward-based method jumps higher with increasing fatigue by exploiting the muscle relaxation during a fall, which results in unrealistic behavior. Finally, unlike previous methods, we allow for intuitive interactive control of various fitness levels as shown here.